Or will our ballistic missile early warning system tell us differently?
7, 6, 5,
Not ours, but theirs.
3, 1.
And if it is theirs, and this is ours? A better design on the drawing board is no immediate effective countermeasure. Our birds must fly when they're required to. The high complexity of modern-day weapon systems demands the closest possible approach to absolute reliability. There is no second chance. So there must be absolute process control during system design and system manufacture. Are these more imports from other lands? Or are they more exports of our own manufacture? Unless we can compete successfully, both at home and abroad, our economy must expand, our industry modernize. To remain strong, to remain free, to enjoy the good life. We also need newer and better aerospace vehicles, and we need them fast. We need newer and better weapons, and we need to get them from design concept and into operation more quickly and at a reasonable cost. We need new and better products for civilian consumption. Products which can compete with foreign goods here at home or in foreign markets. We must have modern manufacturing, as modern as we can make it. Modern manufacturing is a command performance.
Command performance. Well, we usually have enough command of our process to get the performance we want. Of course, it takes a lot of time to get from a set of new drawings to a finished product.
But time is something we don't always have. The period from development to product is growing shorter and shorter. As someone said, time has collapsed. Now let's try this process. Say the complete product is a Type 20K, and we're changing it with a modification of the Type XR. Now, suppose all you needed to do was to say into a transmitter, 3 Type 20K modification XR.
Orders to the plant.
That's right. You merely define what you want, and in a fraction of the time it would take conventionally, your product's manufactured, assembled, and ready to ship. And that component we were talking about is only one of many making up the complete product.
How could you do all that so quickly?
Not only so quickly, but in much less space. You'd need a much larger plant to do this by conventional methods.
Oh, this is not conventional.
Not at all. This is a modern plant. Really modern.
What do you mean by that?
When you give your command over the mic, which may be in the plant or remote, almost anywhere, the information feeds into a voice converter, which translates your language into a language which the computer can understand. The computer analyzes your request, then draws on its store of information to produce a series of tapes, which feed into a production control center. This center not only controls each of the machines, but the flow of parts as well, acting as a scheduling unit. Now all of the manufacturing units are actuated. Basic shapes are routed to production centers for complete processing. Completed components are then checked automatically by inspection machines, then sent on to a robot subassembler. Subassemblies proceed on to a robot for final assembly, and then on to shipping. That's what I call command performance. Of course, I've oversimplified the process a bit.
You mean you've been putting me on, don't you?
Not exactly. This is not as fantastic as you might think. Take the computer, for example. Computers are fairly common today, although we still must talk to them with cards or tape rather than directly. But they're getting more sophisticated all the time. And from this information, a control tape is produced.
Control tape for what?
To control a manufacturing process. Now, these machines are in existence today. Inexpensive tape-controlled drill presses. The more sophisticated turret drill presses. Vertical turret lathes, capable of high accuracy contouring. Tape-controlled engine lathes. With equally exacting contouring and thread-cutting capabilities. High-precision multi-axis profiling mills. Machining centers that change tools, mill, drill, bore, ream, and tap. In many cases, they can complete the entire manufacturing process in just one setting. Fully capable of doing that job of yours we were talking about, and even more. Now, what different tools would you need for this piece?
6 different milling cutters, 4 sizes of drills, 4 reamers, 6 taps, and 4 boring bars.
And where you needed 8 machines to use these tools, the whole batch is loaded into a magazine for use by this one machine. All the instructions to the machine are on a punched tape. The intelligence on the tape tells the machine exactly what to do. This is called numerical control, which is one of the means of using mathematical definitions to furnish intelligence a machine can understand. There are many methods of accomplishing this. However it's done, it certainly shortens the chain of command and greatly reduces the opportunities for a breakdown in communications. There's the same casting you would have started with in your conventional shop. But notice there's only clamps required. The machine itself will even make its fixtures from tape control if necessary. And there you are. All the machining done in only 45 hours. How long would it have taken in your shop?
Oh, about 300 hours to machine and 26 weeks of lead time.
After you tooled up. Remember, the lead time here was only 2 weeks. If you need a second or third or fourth piece, you get them in a matter of hours. All exactly alike. Now that's performance.
What happened to automatic inspection you were dreaming about?
That was no dream. They're already in existence, too. And research and development are making them better all the time. On this machine, a probe is guided by a tape similar to the one used in manufacturing the part. The measurements are recorded for inspection and record.
But you still need an original detailed drawing, don't you?
Not necessarily, but if you want one, it can be made from a numerical control tape too, operating an engineering machine. Often the drawing can be made at the same time the part is being made, using instructions from the same tape.
I notice the loading and removal from the machine is still conventional.
But it needn't be. You'll find automatic loaders and transfer mechanisms on a lot of production lines today. This automatic material handler remembers every sheet in its inventory and will deliver it undamaged in seconds. This robot manipulator will perform a variety of handling operations. It can be easily taught to load, unload, and assemble parts because of its electronic brain. So you see, we have practically all the elements of our plan of the future. It's just a matter of time before someone puts them all together to make the dream a reality. I don't know that anyone has ever produced a crystal ball on one of these machines, but you don't need to be a fortune teller to realize that our success in aerospace depends upon our national capability to produce combat-ready systems with complete reliability. We must produce first, best, and at the lowest possible costs, which are consistent with reliability and reproducibility. This means that we must be able to manufacture from all sorts of new and exotic materials. It means we must be able to produce structural members with a high degree of configuration complexity. It means we must produce with greater dimensional control. Some large rocket engine inducers, for example, can't be produced to design concept by conventional manufacturing methods. It means that we must produce components which have structural integrity. This aircraft bulkhead was built up of over 90 different parts, requiring more than 1,000 rivets and high-strength fasteners. You can imagine how long it took to tool, machine, and assemble all these parts. And you can imagine the possible human error involved. The more modern one-piece bulkheads have greater structural integrity, but they were still expensive. These one-piece bulkheads were first produced by conventional methods, using specially designed tracer-controlled rotary tables with many coordinated overlay templates and tracer patterns. It took 160 hours of machining time to produce one bulkhead, and at considerable cost. The part is now programmed on a numerically controlled skin mill to machine 2 at a time. This requires only 2 sets of vacuum chucks and 9 reels of tape. The time reduced to only 9 hours per part, and the cost reduced by 80%. In addition, there's a 25% reduction in weight. Command performance? I'll say. But you can best get it with numerically controlled machines.
Can this type of control be applied to other types of machines?
Certainly. There are machines that automatically position and punch all types of panels. Machines which build up rocket motor cases by the controlled winding of glass filament. Machines that position connector panels for wiring. Machines that position and make the wiring connections on assembled electrical panels. Machines for drilling printed circuit boards. Machines for inserting the components in these boards. Machines for spot welding, which saves 72% in labor costs. This machine has proved invaluable in spot welding fuselage sections. The more complex fusion welding also can be performed by numerical control. The tape not only controls the positioning and movement of the arc, but also the welding factors, gas flow, current, and the like. In guiding the arc, the control permits blind welding down through one structural member to fuse it with a hidden member below. The result? A stronger weld, a member with more structural integrity. A more reliable weapon system. Tubes can be bent by numerical control also. Tailpipes that fit any car precisely. Or the miles of plumbing used in modern missiles, and all without the need for separate jigs and setup time. most versatile and flexible are the numerical controlled machines. For one-piece or production runs, they're the answer to involved machining operations. And for machine control, you can't beat instructions which are fixed and not subject to human error or emotion. Why, this tape could be sent anywhere in the world to a similar numerically controlled machine. And it would produce a part interchangeable with the one produced here from this tape.
May we backtrack a moment?
Surely.
Just how do the instructions get to the machine in the first place?
Well, let's begin with your own sketch of some part. Make it complicated. We'll hog it out of a block. Let's use master dimension.
Okay. There you are, with all the essential dimensions, but scarcely something a machinist could work from.
That took you about an hour. Now, we'll take this to a programmer as the next step in tape preparation. And there's the program. Now, let's see, that took about an hour and 45 minutes. Add that to the hour for the sketch.
And the 5 minutes it took us to get here.
And the total's 2 hours and 50 minutes.
Those words on there look sort of familiar, but different.
That's right. They're a kind of pidgin English. This information will command the tool to start from the point called set point, which is defined as the point with coordinates 1, 1, 1. With the tool on the right, it is instructed to go right along the line base. At this point in the operation, the tool is sent forward to start cutting a previously defined circle about a previously defined point 2. Now here's that circle on the sketch. You can see it's a language that you can readily understand and use, and one the computer can understand too. As of now, conventional computers do not accept oral commands, so the instructions are put on punched cards or tape. We're moving right along. Just 10 minutes for that job, for a total of about 3 hours. Now the computer operator gives the commands to the computer, which translates them into machine language. And here are the commands we'll take to the machine. We've now spent only 3 hours and 20 minutes. That's really chopping down lead time, isn't it?
Yes. I expect it would have taken me weeks to design and tool for this job.
It might be a good idea to think about modernizing then.
This whole system's called numerical control?
Well, the machines are operated by numerical control. When you talk to a computer, though, well, that's a little higher order of communication. I suppose you might call it symbolic control at that point. But look, your part is already being manufactured. There's your part. Just 4 hours after you started making the sketch. You want to check it out?
You bet. Amazing. Absolutely amazing.
You see, what happened was that the machine did what machines can do best, and humans did what humans can do best. You did the designing, the creating. The programmer planned the process from his knowledge of machining and the particular machine. And being human, you were able to start a chain of command to the machine, a very short and very exact chain. As a result, you obtained a superior performance from the machine, far better than by conventional methods. And you get the same performance time after time, because the commands cannot change.
And that's why you call it command performance.
That's right.
Well, what about the actual joining, forming, or removal of metal? What's new along these lines?
Plenty. Electron beam welding, for one thing. Here, even two dissimilar metals can be permanently fused together by the high-velocity electron bombardment in its vacuum chamber. Electrolytic machining, for another. The cooling holes in this turbine blade were eroded to exacting tolerances by this stem drill. The hollow drill electrodes never touch the material, so they need not be reset or replaced.
Just the opposite of electroplating, huh?
Correct. This finished turbine bucket was shaped from high-temperature material. And here are the shaped electrodes that were used to do it. The process replaces a dozen conventional machines and produces a yearly savings of about 80%. When subjected to enough pressure, metals become plastic and are easily formed. This vertical shear forger produces turbine compressor shafts at a savings of $1,500 per part. Similar machines will turn out shapes such as cylinders, cones, and rocket motor cases from practically any metal, including many of the exotic alloys. Or suppose your product needs formed parts, like this. This machine pre-stresses metal to its yield point and has a tension control system, so that forming is accomplished with high accuracy. This jet engine part was formed from Rene 41 in just 2 minutes, and the savings over conventional methods is 80%. A similar type of process will give you savings of up to 90% on drawn components like this, and permits the use of inexpensive dies. This blank holder, adapted to a conventional press, pre-stresses the metal and makes it more flowable than plastic. By adjusting the stress, almost any metal can be formed using the same die. Normally, 3 draws would be required to produce this part, with 270 hours of handwork for finishing. But here it is, produced in 1 stroke, holding its shape without springback, and maintaining that shape throughout subsequent welding. This hydroform turns out complex, shaped parts in seconds that formerly took hours to fabricate, assemble, and weld. The rubber bladder reduces tooling to only 1 inexpensive die. Want more savings in forming metals? Perhaps electromagnetic metal forming is the answer. This process uses powerful magnetic fields to swage, expand, compress, coin, shear, and assemble conductive metals without mechanical contact with the work. This machine uses the explosive power of man-made lightning to form parts.
What about forging?
How about that? That's high energy rate forging. These machines will deliver a terrific amount of energy in a split second to forge such materials as tungsten or even cast iron, as well as the usual materials. High-tonnage mechanical presses also offer great savings in the production of precision forgings. For testing electronic systems, there's automatic testing equipment. Here's a complete checkout of a wiring harness. This machine checks missiles, computers, servo systems, and the like. The results of the tests can be recorded on a printed readout. And the savings? Well, in addition to the time, this piece of equipment replaces 150 separate pieces of test equipment required on many of the complicated checkouts. Imagine what all these methods of modern manufacturing are going to do for the designers. And of course, you've seen only a few of the many new methods available today. No need for them to be limited by the restrictions of conventional manufacturing. They can now design a part to do the best job without compromise with manufacturing limitations. I doubt if there's a machinist in the world who could have turned out this part and met the required specifications. Yet it's a vital part, and I know that without modern machining, it could never have been produced in time to get our missiles in operation on schedule. And believe me, we must be on schedule in these areas. You know, today in some sections of the world, the smelting of iron is still a primitive process. And metal forming is equally crude. But some of our manufacturing processes still border on the primitive. While even the most modern standard machine tools are efficient for general applications, they will not readily accept the numerical control input so vital for the effective production of aerospace vehicles. We must modernize our manufacturing methods and go from design concept to finished product as quickly as possible. We must keep the wheels turning the best way we know how. We must apply what we know today and search for ever better methods. This is a command performance for the survival of industry and our country.
Say, do you still have that clipboard?
Sure. Here it is. Why?
I want to write myself a note so I won't forget something. See? This is going to be a command performance, too.
Good idea. Because the Defense Department expects its contractors to maintain a modern base in their facilities. In keeping with the advance of aerospace technology, we need the productivity, reliability, and repeatability that only modern manufacturing can provide. And we all need the savings which can be effected in both time and money. Ours? Or will our ballistic missile early warning system tell us differently?
7, 6, 5,
Not ours, but theirs.
3, 1,
And if it is theirs, and this is ours? A better design on the drawing board is no immediate effective countermeasure. Our birds must fly when they're required to. The high complexity of modern-day weapon systems demands the closest possible approach to absolute reliability. Modern manufacturing is a command performance.
Command performance. Well, we usually have enough command of our process to get the performance we want. Of course, it takes a lot of time to get from a set of new drawings to a finished product.
But time is something we don't always have. The period from development to product is growing shorter and shorter. As someone said, time has collapsed. Now let's try this process. Say the complete... We must have modern manufacturing, as modern as we can make it. We also need newer and better aerospace vehicles, and we need them fast. We need newer and better weapons, and we need to get them from design concept and into operation more quickly and at a reasonable cost. We need new and better products for civilian consumption, products which can compete with foreign goods here at home or in foreign markets. There is no second chance. So there must be absolute process control during system design and system manufacture. Are these more imports from other lands? Or are they more exports of our own manufacture? Unless we can compete successfully, both at home and abroad, our economy must expand. Our industry modernize. To remain strong, to remain free, to enjoy the good life,